Welcome to this deep dive into self-healing materials. We are moving from static structures to dynamic, autonomous damage management systems, as illustrated by the self-repairing cracks shown here. The paradigm is shifting from damage prevention to active damage management. Traditional engineering focuses on preventing flaws, while self-healing systems, inspired by natural repair processes like bone and skin healing, autonomously restore original functionality. Self-healing follows 5 universal stages. First, crack induction, where mechanical load causes a microcrack. Second, a trigger, like the damage itself or heat, activates the system. Third, mobile phase generation transports material to the damage site. Fourth, crack closure involves physical or chemical bonding across the gap. Finally, immobilization occurs as the phase solidifies, restoring mechanical properties. These steps define how materials autonomously fix themselves. The self-healing taxonomy classifies materials as autonomic or non-autonomic. Autonomic systems are triggered solely by damage, while non-autonomic systems require external triggers like heat or light. Autonomic systems are further divided into extrinsic and intrinsic types. Extrinsic architecture uses microencapsulation. Urea formaldehyde microcapsules contain a healing agent in an epoxy matrix. A crack ruptures the shells, releasing the agent to contact a catalyst and polymerize, bonding the crack surfaces. The limitation is single-cycle healing due to reservoir depletion. Extrinsic architecture 2 uses vascular networks, modeled after biological circulatory systems. Hollow fibers containing reactive fluid release repairing chemical when mechanical trauma removes the coating or fiber wall. This allows for multi-cycle healing by continuously supplying reagents. Intrinsic systems take an embedded agent-free approach. Healing relies on 5 steps: surface rearrangement, surface approach, wetting, diffusion, and randomization, leading to complete interchain integration and material recovery. Intrinsic physical healing uses the sigma lock mechanism. Interchain junctions in alternating copolymers self-heal upon separation. Lateral dipolar forces between aromatic groups and aliphatic ends create an autonomous realigning force, enhanced by van der Waals stabilization. Intrinsic chemical healing utilizes dynamic covalent kinetics, such as the reversible Diels-Alder reaction. An engineering trick uses an off-stoichiometric design to maximize reactive encounters at the fracture surface, enabling complete structural recovery within hours at room temperature. Radical recoupling and cleavage is another intrinsic chemical healing method. Mechanical damage cleaves bonds, generating stable free radicals. UV light can trigger healing in polyurethane networks, provided the radicals have low oxygen sensitivity for successful chain end rebonding. Restoration is quantified using mechanical measurement tests, like the tapered double cantilever beam. Metrics include fracture toughness recovery and fatigue healing, which monitors subcritical crack growth under cyclic stress, showing localized retardation and pre-crack healing. Constitutive modeling of self-healing elements uses models like Kelvin Voigt and Maxwell. The reversible crack element uses an anharmonic potential function, where mechanical work is reversibly stored in newly created surfaces, driving the healing force. Beyond polymers, inorganic systems are being developed. Metals and ceramics require high-temperature triggers. Shape memory alloys physically close cracks. Concrete utilizes biomineralization, where embedded bacteria mend microcracks at ambient temperatures. Self-healing materials have real-world applications in drug delivery, energy storage, aerospace, defense, and wearables like flexible e-skin. The future targets structural composites capable of 100% strength recovery, infinite cycles, and autonomous triggers at ambient temperatures. This video will explore viscoelastic modeling by translating the mechanical analogs of springs and dashpots into continuum mechanics. We will look at how the elastic response of a spring and the time-dependent viscous behavior of a dashpot form the foundation of these models. First, let's establish a translation dictionary. We bridge discrete physics concepts like force and displacement with continuum mechanics variables such as stress and strain. The spring translates to elastic modulus, and the dashpot corresponds to viscosity. We begin with Kelvin Voigt kinematics, which uses a parallel architecture. In this configuration, the elements share the same strain as they are rigidly connected. The total stress is the sum of the stress in the spring and the dashpot. Deriving the Kelvin Voigt constitutive equation starts with the force balance. Substituting the constitutive laws and defining the time constant tau as viscosity over elastic modulus leads us to the fundamental Kelvin Voigt equation. The creep test applies a constant stress. For the Kelvin-Voigt model, the strain rises exponentially, approaching an asymptotic limit. This behavior reflects a solid-like response. We can extract parameters from the creep test data. The elastic modulus is found from the asymptotic strain. The time constant is the time at which the strain reaches 63.2% of the asymptote, and viscosity is calculated using these values. For numerical applications, we can use a discrete time-step update to approximate the strain rate. This allows for simulating the Kelvin-Voigt strain response, as shown in this 5-second worked example. Next, we examine Maxwell kinematics, which features a series architecture. In this setup, the stress is the same across both components, and the total strain is the sum of the strains in the spring and dashpot. To derive the Maxwell constitutive equation, we differentiate the total strain with respect to time, substitute the constitutive laws, and rearrange with the time constant. This results in the fundamental Maxwell equation. In a stress relaxation test, a constant strain is applied. Due to the dashpot's inability to deform instantly, the spring takes all the initial strain. The stress then decays exponentially over time. Parameter extraction for the Maxwell model begins with the initial stress peak to find the elastic modulus. The time constant is where the stress decays to about 36.8% of its initial value, and viscosity is calculated from the modulus and time constant. Contrasting this, the Maxwell creep test under step stress shows an instantaneous elastic jump followed by a linear viscous flow that continues indefinitely, indicating fluid-like behavior. We can simulate Maxwell relaxation using a strain-driven discrete update. This allows us to predict the stress response over time, as demonstrated in this 5-second numerical example. In synthesis, the Kelvin-Voigt model features equal strain and additive stress, modeling solid-like memory where creep strain reaches an asymptote. The Maxwell model, with equal stress and additive strain, models fluid-like yielding as stress relaxes to zero and creep flows infinitely. This video details modeling a reversible crack element, transitioning from anharmonic potentials to self-healing constitutive recipes. The model utilizes anharmonic potential energy, a reversible crack element, and viscoelastic self-healing, while accounting for fracture and energy dissipation. The cohesive zone element converts potentials into traction. The reversible crack element links crack opening to stress-like force. Traction is the mathematical derivative of the potential, and the reversibility requirement means unloading follows the same potential curve with zero dissipation. We define the kinematic state variable using a reference volume with the stretch ratio and a cohesive area with crack opening displacement. For the reference volume, nominal stress is related to the derivative of the potential. For the cohesive area, traction is the derivative of the cohesive potential. Fracture energy is the area under the traction separation curve. This is the work per area stored in creating the surfaces. Because the element is reversible, this energy is stored and can be fully released during closure. The traction separation law has 3 zones. Zone 1 is initial stiffness at small strains. Zone 2 is peak stress, reaching maximum load-bearing capacity. Zone 3 is the softening region where traction decreases as the crack opens and bonds break. Anharmonic potentials drive the softening behavior. Anharmonic changes because the second derivative, or tangent stiffness, changes with deformation. Before the peak, tangent stiffness is positive. At the peak, it is 0. In the softening region, it becomes negative. We use the Morse-type cohesive law. Differentiating the potential field yields the traction formula. This specific anharmonic potential naturally produces the required stiff, peak, and softening behavior. The Morse model has key mathematical properties for peak location, peak traction, and energy consistency. The peak location and traction are derived from maximizing the traction function, and the integral of traction defines the fracture energy. Reversibility produces the healing force. When unloading, the system follows the exact same traction law without creating new dissipation. The element actively releases its stored surface energy, which manifests as a traction force that actively closes the crack. The system integration workflow involves 3 steps. Step 1, specify loading, defining the kinematic variable over time. Step 2, compute traction, calculating stress from the potential's derivative. Step 3, constitutive coupling, combining the reversible crack element with viscoelastic elements. Step 1 involves converting macroscopic strain to local opening. An effective length scale parameter, LF, acts as the critical bridge, converting dimensionless macroscopic strain into the physical, localized opening displacement. Step 3 outlines constitutive coupling strategies. Parallel coupling, standard for matrix plus damage, means the same strain and stresses add up. Series coupling, an alternative, means the same stress and strains add up. The total stress is the sum of the viscoelastic backbone stress and the reversible cohesive element traction. The viscoelastic module captures time dependence. The reversible cohesive element module captures damage and recovery through stored surface energy, such as the Morse potential. The executable simulation loop involves 6 steps. First, input the strain. Second, compute the strain rate. Third, compute the viscoelastic stress. Fourth, scale the kinematics to compute opening. Fifth, compute the cohesive traction. Finally, output the total state stress. The architectural summary covers 4 quadrants: core, kinematics, and energy, the anharmonic curve, Morse implementation, and constitutive execution. These components define the cohesive healing models.